All right. So we're working on this notebook for potential flows. Okay. We already just put in I don't remain already. Okay. Potential flows in class. Okay. Okay. So we already kind of imported a bunch of things. This is a styling format that you can grab actually from my from one of my GitHub repositories. It makes for beautiful styling, and these are some basic things that I want to import. The math library, probably not going to need it. We'll just get everything from NumPy, Matplotlib, plotting thing, right? Okay, if you have questions, ask me if you're new to Python, but I'm going to assume that most of you have basic familiarity with Python. Okay, so the way I'm going to do this, I'm going to define a function for the uniform stream and a function for the source stream, and in the future we're going to add a doublet and a vortex, and each of those functions is going to return to me the Cartesian velocity components, u and v, as well as the stream function. So every one of those functions, Python functions, is going to return three things, u, v, and psi in Cartesian coordinates. Okay, so we'll start by doing uniform, so def uniform. And I am going to assume that the function is going to take x and y coordinates in the plane. So those are the x, y coordinates in the plane. For the uniform stream, what do I need? I need a velocity at which the stream is moving. So that will be u. I'm going to assume, make it default to 1. And I'm going to assume an angle alpha equal to 0. Okay? So these are the coordinates, x, y, and u and alpha are defaulted. So we know that u in this case is u times cosine of alpha, agreed, and v is u times sine alpha, and psi is simply u times y cosine y times np dot cosine alpha. I know I can use the, but that's okay. Minus x times np dot sine alpha. Okay, and then I'm just going to return them. Return u, v, psi. So if I call uniform stream and give it x and y and these guys, it's going to return three quantities. The first quantity is u, the second quantity is v, the third quantity is psi. Okay, so now let's define the define a uniform stream. Okay, define source / sink. Okay, and let's call it source, because we're mostly going to be using sources. We're going to be using sinks too. Okay, so this as well will take x, y. Okay, now we don't know what those are because we're just going to plot them everywhere in the plane, right? So there's no default for those. I'm going to assume a source strength of 1. Okay, this could be a negative value. And what else do I need? Location. Okay, so I'm going to assume it's by default located at 0. Okay, at the origin. Agreed? Oops. Pardon me? It can be y0. Oh, it has to be y0 because we already defined y. Okay. MP. So let's first. So we know now the stream function. We know this case in terms of r and theta. So what I'm going to do, I'm going to define r and theta in terms of x and y, and then I'm just going to use the r theta form and just it will automatically substitute the Cartesian coordinates. So r is n numpy dot square root of x minus x0 squared plus y minus y0 squared. Okay, and theta is equal mp dot arctan 2. You want to use the second inverse tan so that it gives you the appropriate quadrant. Okay, so if you're between 0 and pi over 2, and pi, the standard arctan doesn't make that distinction. Okay, so you want to know this arctan 2 will give you which quadrant you're in. Okay, and this would be y minus y0. We did this last time, remember? Over x minus x0. Okay? Now, x and y, they're actually numpy arrays. Or they could be a value, but they're actually, we're going to pass in full numpy arrays for the entire plane. Okay? Now we can define ur is m over 2 pi r, agreed? And then ux, so u theta is 0, there's no u theta. Now ux is ur times cosine theta. And then uy is ur times sine theta. See what happened here? Rather than having nasty long expressions of x and y and whatever, I just define r theta in terms of x and y, and then define the other quantities in terms of r and theta. And finally, psi expressed in the Cartesian plane is m over 2 over pi over 2 pi times theta. Okay? And then return ux, uy, psi. Okay, great. So now we have these two guys defined. Let's go ahead and create a couple of plots. So first we need to, source. So now watch for the nice styling. Source in uniform stream. Okay. Okay. What?
Is it like HTML you used to do that with?
Yes, yes. Yeah. I copied it from someone else, and then I modified some of the things to make them fit the University of Utah kind of coloring, etc. Yeah. Okay, so we will add a uniform stream and a source located at the origin. Okay, just some text. All right. Okay, so but first we need to define a grid. Okay, first, let's see, where's my cursor? Okay. But first, I'm not gonna talk a lot, put a lot of text here because we don't have time, but I encourage you to type as you do your notebooks, because if you're like me, you don't type as you do your notebooks, and then you come back to them after a year, you're like, who, what? But first we need to define a grid for the x, y coordinates in the plane, okay? In the plane. So I'm gonna do, I'm gonna assume we're gonna do maybe, let's say 150 points, so n 150 points in x and y. And for the domain, we're gonna do, let's do x0 equal, let's do x0 is equal to -2. Actually, we can deal with that later. Okay, so let's do x0 is equal from -2. We're going to define our plane for plotting from -2. So x0, x1 is going to be 3, let's say, and y0 is going to be. So these are not the location of the source, etc. It doesn't. Those numbers are different than what's here. This is just a dummy argument. Whatever you pass here is going to be embedded here. This x0 is not going to be seen inside unless you don't redefine it. Okay, y0 would be -1 and y1 would be 1. And then let's create a linear space. So x is equal numpy.linspace. So I'm going to create a set of uniformly distributed points going from x0 to x1, 150 points going from x0 to x1, and then y, a set of also uniformly structured points going from y0 to y1, this is spaced by n over x1 minus x0 over n, so 150 points in each direction. So you can see print x. If you print x, that's what you're getting. Okay, we're just creating coordinates in the x, coordinates in the y. Now you need to combine them together to create a grid. You need to create a mesh. Okay, because right now they're disconnected. There's x and there's y. So now you need to create pairs. For every x, you got to get all the y's, right? So you need to have pairs, tuples, okay? And you do this with mesh grid. I think Python, MATLAB has the same thing. So I'm going to call those capital X and Y, and that's called mesh grid X, Y, okay? And that's what you'll get. So you could do plt.contour. Okay, so you kind of see how X is the same along Y, okay, but it changes in X. Anyway, okay, so those are our X and Y. Now we can add the source and the stream. So let's say U is 1.0, and then for the source, start by computing. For the free stream, start by computing the free stream. So we'll assume U is 1 meter per second, and U free stream, U V. So because I'm going to be superimposing velocities and stream functions, I'm going to be naming them U0, V0, C0 for one type of flow, U1, V1, C1, U2, V2, C2, and so on. Okay, for each type of flow that we're going to add. Okay. All right. So all I have to do is say call uniform, and then all I need to do is pass. So see, this is the function signature. We'll pass X and Y, and U. Alpha will automatically be 0. Okay. And then now add the source. Okay. So let's assume the source strength is 1.0. Source strength, okay, and then U1, V1, C1 is equal to source. What's the function signature? So we need X, Y, and M. We give it M, right? And I'm going to assume it's located at 0, 0, so I'm not going to touch X0 and Y0. Okay, total velocity. U is equal to U0 plus U1, V is equal to V0 plus V1, and C, so that's the total, is equal to C0 plus C1. Makes sense? Okay. Okay, we have an error over here. What is it saying? Invalid number of arguments. Oh, okay. Yeah, this is wrong. The arctan, you can't put a divide, you have to put a comma. Okay, great. So now let's do some plots. Make some beautiful plots. Okay. So first, let's create a figure. We'll give it a size. Let's see, fig size 6, 3.5. I usually try to use the golden ratio for figure sizes. Anyway, just for scaling. Okay. So the way I'm going to plot the streamlines is I'm going to plot, there's a feature in Python, in Matplotlib called streamplot. It takes a vector field and computes streamlines. And I claim that that's superior to just plotting the contours of the stream function. Okay, so that's what we're going to do. Let's do plt.streamplot, and we need to give it the coordinates x, y, and then we have u and v. And so if we do this just as is, let's see what happens. Oh, look at that. That's not bad. Okay. Now we can manipulate. Let's make this a little bit better. So I'm going to increase this to maybe 7 and 3.85. Yeah, we can see it better. So you can see the vector graphics. You see this? Any way you scale it, it's just going to look beautiful. Anyway, okay. So we can manipulate this a little bit. We can add density of the streamlines. You can do more streamlines, become really crowded, right? Or just kind of lower the density, maybe even 0.9. Okay. Maybe actually 1 was just perfect. Okay, and let's put a line width. And these are settings you can kind of learn on your own. Okay, I'm just like every time I Google, I have to Google it. Okay, so that's great. Let's now make it look a little bit nicer. So let's add the location of the source. Okay, so with this, you're gonna do plt.scatter. Okay, and the location of the source is 0, 0, and we'll make it red. Color equal red, and size equal 20, and we'll give it a marker equal O. Okay, so there's your source location, 30. Okay, now let's add the stagnation point. Okay, so add plot source location, plot stagnation point, plot location of stagnation point. If I remember my English teacher teaching me proper English. Okay, so this is gonna be located at minus b, and b was equal what to m over 2 pi u, right? Okay, so minus b, so x is minus b, y is 0, and color, okay, let's just copy from this guy. Scroll this up a little bit. Okay, let's make it green.
You change the point.
Okay, okay. Okay, right, so this is stagnation point. Okay, so now I want to plot, I told you that there's a little trick to plot the shape of the body. So, I mean, it does look like it's a flow over a solid body, right? So there's these streamlines coming in and then they diverge, and so I want to plot this shape. And honestly, I find it a little bit annoying to have to plot the solution for the shape of the body. So instead, what I'm gonna do, I'm gonna do the contours of the stream function. So we have the full stream function. We can do the contour plot of the stream function, but I'm only gonna select those two streamlines that pass through the stagnation point. Remember, the value of the stream function at the stagnation point was m over 2. And that's what I'm going to do. But first, let me show you how the streamlines would look like, how the contour would look like for the stream function. Contour f, x, y, c. Okay. This is kind of the shape of the body. So what we're going to do here, now we're going to take this, we're going to do the same thing. Plot boundary of half body. Okay, and we will do plt.contour. Okay, and x, y, c, right, just like we did before. However, now we're just gonna do the levels, just two levels, m over 2 and minus m over 2, because there's two values for the streamline. If one above is m over 2, the one below is minus m over 2. Okay, and let's give it colors equal red. Okay, and line width is equal to 2, and it throws an error. Okay, contour, what? Color is red. This is C, level equal. Oh, did I define M? I did define M. So yeah, that's so minus M over 2 and M over 2 shouldn't matter. And then colors, line width. There you go. Okay, so line styles, of course, because everything is plural. Okay, there you go. Cool, huh? Yes, sir.
So I just have a question about so like we have back when they looked different, when one was dashed and the other one wasn't. It seemed
a little bit different. That's a calculational thing. Yeah.
So I'm wondering, like, like you see how they converge and then they like meet at the same place going off to the left. So do they have the same value? Do those
They
two
do
vectors have the same value there?
Well, yeah, they will have the same value, but they're like kind of just. So one of them is going to diverge up, and one of them is going to diverge down. But over here, they're very closely spaced to each other.
Yeah.
Because remember, that's only a value. So if you take the stream function and evaluate it at theta equal pi for r greater than b, then they will have the same value.
Okay.
Okay. But then they're gonna just diverge here. I mean, that's something we can try. We can look at. But they should have. Yeah, they should have. They could not have the same. It could be m over 2 and minus m over 2. That's fine. But actually, the value of the stream function should be m over 2. Okay, but for plotting, you have to do the plus m over 2 and the minus m over 2.
Okay.
Okay, well, that's time now. But now think what would happen if we added a source. So let's just kind of give you a preview of what will come in next. Okay, so now let's say we want to add source plus sink in uniform stream. So what do you think is going to happen? Let's do these guys here. Okay. It's not, sometimes it doesn't allow me to copy. Okay, so what I'm going to do, I'm going to add a source located at x source 0 is located at minus, okay, let me define a is equal minus 0.5. We're going to put a source at minus 0.5. Now add a source at minus a. Sorry. Source strength. Okay. Add a source at, so x0 will be equal to minus a. Okay. And then add a sink. Now add a sink at a. Okay. It will have the same strength. Our sink was same strength as source at a. So it will be x0a, agreed, and minus m over here. And this would be u2, v2, and c2. So we would add here plus u2, plus v2, plus c2. Okay? What do you think is going to happen? Pardon me?
It will give us the zucchini.
No. Well, if you change the strength of the sink, probably give you the zucchini. Okay, but now this the stagnation point is not going to be valid anymore in this case, because I know, and this guy is not going to be valid. What's going to happen? Look at that. Okay, so now let's add plot source location. It's going to be at minus a, and plot sink location is going to be at a. So now we added a source and a sink, okay, and that's what it gave us, okay. So this looks like the flow over an oval, and this is called a Rankine oval, okay. So we can space them a little bit further apart. We'll do this next time very quickly. Let's say put them further apart, becomes Rankine oval, okay. But the stagnation points, they're going to be a little bit harder to calculate. We'll just give you the formula for those. But you will notice that in this case, the stream function that defines the body is actually equal to 0. So if we put 0.0, look at that. And from that, you can calculate the shape of the body, okay? You can calculate the shape of the body. Like we did before. Anyway, any questions? So we'll continue next time. We'll do, we want to get to the flow over the cylinder. We're going to bring the source and the sink ever so closely together. and that's going to create a doublet. So then we will do the doublet, which is the uniform flow over cylinder. Uniform stream plus doublet gives you over cylinder. And then if we add a vortex to the cylinder, that gives you an approximation to the flow over a rotating cylinder, which is going to kind of twist the streamlines a little bit, and it gives you a theta component of velocity. Okay? Thank you.